There's actually an easy way to keep track of how many times a chemical reaction has taken place if you have an initial amount of each substance. It's called an ice table. First, we're going to keep track of the initial amount, what we have of these two things, and then we're going to keep track of the change, which comes from these coefficients here, and then we're going to figure out what happens at the end of the whole reaction. It's kind of interesting. So let's start with 28 grams of the nitrogen, and we'll start with 12 grams of the hydrogen. Now we got to convert this to moles, so we'll use the molar mass, and we'll go ahead and do 28 grams on the bottom and the moles on top over here. Over here it would be 2 grams on the bottom, moles on top. And if we try to solve these, obviously this would be equal to 1 mole over here on the left, and this would be equal to 6 moles for the hydrogen. So we have 1 mole of nitrogen in the beginning and 6 moles of hydrogen in the beginning. Based off of this, you can kind of start to figure out how many times you can really do this, but let's keep going. So over here, we would start with 0 products because, well, it's the product, so you're not going to have anything at the beginning. So you only have the initial amounts. Now for the change, we're just going to take that directly from the coefficient. So we're going to go -1 over here, -3, because this is the reacted side, so we're taking away stuff from that side, and then +2 over here, because this is the product, so you're going to add stuff to that side, and then we're going to put the same variable across all 3 of these. We'll just call it x. It's going to tell us how many times that particular thing happened with our initial amounts. So on this last line, we're actually just going to set up 3 different equations. So we've got 1 minus 1x. Here we've got 6 minus 3x, 6 minus 3x. And over here we have the 0 plus 2x, 0 plus 2x. And so now we have our 3 equations. Well, they're not equations yet, because we have to set them equal to something. Well, this is supposed to be the equilibrium stage, so let's figure out what happens once the reaction has reached equilibrium. And in this case, we'll assume that the reaction is complete at that stage. These things should be equal to 0, right? The reactants should be all completely used up. And the product side, it should be equal to, well, whatever happened here. So let's finish this equation. We'll just call that 2x. Okay, so we're going to set the left sides equal to 0 if the reaction is completed. And then we're going to set the right side equal to our equation. Well, we're going to solve that at least. So now we can actually see how many times the reaction was able to run with how much we started with. So over here, we'd be able to see that x equals 1. So we were able to run the nitrogen through this 1 time. We got 1 reaction out of the nitrogen. Over here, since we see that x equals 2, then we know that with 12 grams, we could have done this thing twice. So we got 2 reactions from the hydrogen with 12 grams. So what this is telling us is that if we have 28 grams of the nitrogen over here, then that was able to get us 1 reaction. You'd get 2 NH3s out of this once you plug in 1 into that equation, or you just count it up. And over here you'd see 12 grams. 12 grams, if you run that into this equation for the hydrogen, then you would get 4 NH3s. And so basically this is what this chart is telling us, and it's giving us a whole bunch of information in a neat, organized way. So if you could fill this stuff out, it's pretty nice. So this chart immediately highlights the limiting reactant, which is going to be basically the bottleneck of this reaction. And you'll see it would be the nitrogen, because we could only run that 1 time. It usually will be sort of given a limited amount of grams or moles. Now the theoretical yield is going to be basically the max calculated yield from your equations, but usually this will be in a grams form or moles form or something. And the percent yield would basically be the ratio of what you actually got, which was your experimental yield, which you got in the lab, divided by your theoretical yield, which is what you calculated, and that would give you the percentage, so you could find the percent yield. Now let's say we had 18 grams of oxygen and we added in 2 grams of hydrogen. Then we would actually realize that an H2O molecule only has 18 grams. So you'd get 18 grams of this H2O molecule, and then you'd have 2 grams of leftover O. So this right here is the excess, which is essentially just leftover stuff after a chemical reaction has taken place. So there's this big word, the aqueous solution, and that basically just means something is dissolved in water. So we could say that water is the solvent. And what that looks like is, let's say we have the salt, NaCl, and basically these things are going to kind of break apart, and the reason is because we've got this water molecule here, and we should kind of know that's the oxygen there. It's going to be a pretty strong negative, and so it's going to kind of want to be attracted to this positive Na, and so you might see a couple of them kind of drag away the Na, all right, versus the wings are going to be more pointing, first of all, as far away as they can from the Na plus, but at the same time as close as they can get to the Cl. So you're going to see all the positive little sides, those wings, they're going to be attracted to the Cl's, and they're going to drag the Cl away, and then all the negatives are going to be attracted to the NAs, and they're basically just going to pull that apart. So you kind of have these water molecules all fighting for the Cl's and the NAs, and they're just kind of like pulling each other apart like that. So it's kind of cool. So this is essentially how stuff gets dissolved. The NaCl in this case was the solute. The solute gets dissolved, and the solvent, which was the water, the solvent dissolves the solute. It dissolves the solute. And keep in mind, the solute is going to be the lowest percentage of solution, and the solvent is the highest percentage of the solution. And as you can see, this is just basically ripping apart the NaCl. Now, if you're trying to prepare an aqueous solution in a lab, then you want to follow the 3Ds. First, you'll dissolve. So just take the solid that you have and dissolve it in a little bit of water, so that it's just enough you can mix it around and dissolve pretty much all of it that you can. And then you're going to dilute that solution. You start pouring in up until pretty close to the amount that you actually want. And then at the end, you would want to use a dropper to be able to finely tune the exact amount, so it's not doesn't go over, because it's difficult to get the exact amount when you're doing this. So dissolve, dilute, and then dropper. Now let's compare the 4 different types of concentrations. So we have molarity, which is going to be the mole of the solute divided by the liters of the solvent. And for molality, this is going to be the moles of the solute divided by kilograms of solvent. So basically, it's the same kind of concept, but just different denominators. You just have to make a quick conversion. Now, as far as density and mass percentage, well, density is going to be grams of solute divided by the milliliters of the solution. And the mass percentage is going to be the grams of solute divided by the grams of the solution. You just have to remember that the solvent and the solution are different things. The solvent is just going to be the liquid by itself, whereas the solution is going to include the solute as well. So you're just going to have to kind of add up everything on the bottom here, whereas this is just going to be the liquid by itself. And so you can see that the density and mass percentage are pretty similar. Grams over milliliters, grams over grams. Just have to make a quick conversion there. Now, NaCl, the salt, was actually something that we call a strong electrolyte. So that actually completely dissociates. So we could represent that with an equation, H2O plus NaCl becomes Na plus Cl minus plus the H2O. And let's try to recognize these states as well. We have the liquid version of H2O and the solid version of salt over here. But afterwards it becomes aqueous over here because it was dissolved in water. And as you can see, it completely dissociates. So it started as one compound, the NaCl, and then over here it breaks apart into two different ions. Even though it's still salt water, these things have separated and they're basically free to move around anywhere. And that makes them conductive. They can conduct electricity because, well, they've got free-flowing ions and stuff. So that's kind of cool. Now, a weak electrolyte is only going to have partial ionization. That's just another word for this whole dissociation process. So we're going to have maybe salt was a real electrolyte. A weak electrolyte is going to be more like a vinegar. So we'll see what the equation for vinegar would be. HC2H3O2. So this is basically acetic acid. And then we have put that in H2O. And we're going to have a partial ionization here. That's the double arrow, which means the reaction happens in both directions. And over here, we're going to have C2H3O2. And here we're going to have negative, and then we have a plus H3O. This is hydronium. And so as you can see, we've lost the H, and it becomes an H plus ion, because this is an acid, so it will lose the H plus ion. But we're left with this molecular compound here, so it doesn't break apart easily. It doesn't really have ionic bonds that can just break apart. It's more of just like a molecular compound, and so it's a little bit harder to break apart. So over here we're going to put aqueous for the acetic acid because it's dissolved in water, and over here we have the liquid form of water. Well, on this side we actually have the acetate ion. This can be the negative over here, so that's going to be aqueous. And over here, this is the hydronium plus ion, and it's again going to be aqueous. So it's just kind of the partial ionization of vinegar, and this happens back and forth. So these things kind of keep breaking apart, returning back into these compounds, and then forming back into there, and kind of have this partial ionization happening. Now let's see what the non-electrolytes do, because they do not ionize. So they don't break apart at all. That'd be something more like sugar. So let's see the equation for that. We'd have C12H22O11 plus H2O. And that will just turn into C12H22O11 plus H2O. But there's one main difference. On this side, we had solid sugar, and on this side we have aqueous sugar because it was dissolved in water. So that is really the only difference there. So what's really happening here on this level is, let's go back to what was going on over here. Instead of just being the ion, we have the whole chunk. And that whole chunk is being dragged around by the water molecules. So it's basically just dispersing all of these things. Instead of them being all crystallized up into a solid chunk, it's just dispersing all those into the water. That's what's going on when things don't ionize and when they do ionize. So let's compare strong acids and bases and weak acids and bases. The strong acids and bases are going to completely dissociate. So that's going to be something more like the HCl. If we had hydrochloric acid, it's going to be the same thing as NaCl. The H plus is going to break off and the Cl is going to be left alone. But there's going to be some weak acids and bases. For example, the vinegar over here. This is going to undergo the partial ionization. So we kind of have the equation here, but that's, you can see how HC2H3O2 it's just going to lose the H plus ion, and then the rest of it is going to stick together, and it's also going to dissociate, but it's just going to stick together. as a whole ion by itself. And let's also compare what acids and bases are, because we could see how acids will shed H plus ions, and bases are going to kind of do the same thing but with OH minus ions instead. That's the difference between acids and bases. Now I've marked these things in red because there's going to be charts, lists, and tables of the strong acids and bases that can completely dissociate, and then the soluble and insoluble compounds. Well, the soluble ones can dissolve, and the insoluble ones cannot dissolve. So we have some examples of things that can dissolve over here. We started with the solid version, and even if it didn't completely dissociate, it still dissolved, and you know, those molecules got separated by the water. So that would be what it means to dissolve or not dissolve. So the soluble compounds, these guys become AQs. They're aqueous, so that means they've been dissolved in the water. Whereas the insoluble ones, these things remain as a solid. They don't dissolve, they don't become aqueous. Now let's see if we can actually take two liquids and turn them into a solid somehow. That would be called a precipitation reaction. This is when a solid forms, and you just have to follow the solubility table, the rules for this. Let's look at an example of a molecular equation for the precipitation reaction. So we'll have silver nitrate along with sodium chloride, and that's just going to become an insoluble silver chloride and sodium nitrate. So on the left side we have aqueous solutions, AQ. On the right side, this remains aqueous, but this is a solid because silver chloride is insoluble. Or rather, silver is insoluble in chlorine. Usually things can dissolve in chlorine. Let's try writing the total ionic equation here. So since these things are aqueous, they're going to completely dissociate. So we're going to put Ag plus and NO3 minus, and then we've got Na plus and Cl minus, and that's going to become, well, we still have this thing, the AgCl. That's a solid. That's not going to break apart. Then we also have Na plus and NO3 minus. So all these things broke apart. Let's keep track of these things for now. These are all aqueous compounds, and the only thing that is a solid is this one. We can kind of see how this equation is just about the same on both sides, but there's a little bit of differences. So let's see if we could spot that. Let's go ahead and delete what is the same on both sides, and we've noticed that we've basically combined these two compounds, and these are different on that side than they are on that side, whereas these things are the same on both sides, so we can get rid of those. So we should be able to come up with a net ionic equation, which would say that silver plus chlorine forms silver chloride. And that makes a lot of sense. So we'll go ahead and put AQ, and the solid over here. That would be what actually happened during this reaction. We did see that the sodium and the nitrate were essentially spectators here, kind of just, you know, hanging around in the water, not really doing anything. Here's a couple more common reactions that we might encounter. We've got recombination, synthesis. Let's say we've got some hydrogen plus some oxygen. That's just going to form some water. This is a combination, adding them together. Decomposition would be breaking them apart. So let's say 2 mercury oxide becomes 2 mercuries and some oxygen over here. Okay, that's a decomposition, breaking things apart. The single replacement, there's actually a reactivity table we have to follow for this to make sure that it actually does happen, because some compounds are more reactive than others, so they might not actually want to, like whichever one is the most reactive is going to end up being as part of the combination over here that we make. So from this, we can basically tell that magnesium is more active than the hydrogen. So it's going to displace that and basically take over that spot. While the single replacements are going to be more based off the reactivity table, the double displacements are more based off of the solubility rules. So let's try one between lead 2 nitrate and we need some potassium iodide, and then that's just going to become lead, well, it's still lead 2 iodide and some potassium nitrate. 3. Okay, so we started with the aqueous compounds. This actually became a solid, and there was a precipitate that formed, whereas we had another aqueous compound over there. That's going to be the double displacements. For the gas evolution, let's try mixing baking soda, which is sodium bicarbonate, and vinegar, which is acetic acid. And then that's just going to form sodium acetate over here, and liquid water, and carbon dioxide. So we started off with the aqueous, and this is still aqueous. This is a liquid water, and we have a gas forming over here in the form of carbon dioxide. Now for my favorite reaction is the redox reduction. That's going to be when things are gaining or losing electrons, which usually happens during these ionization processes. But let's go ahead and count up the oxidation states of these compounds. So here we'll start with realizing that, well, we have to crisscross these. We should be getting a +3 for the iron and a -2 for the oxygen. Let's realize there are 2 irons, so this technically is going to be a +6, and there are 3 oxygens. This would add up to be a -6. If we put parentheses around all this, this compound should be equal to 0 net charge, because, well, that's just what that compound is, that's the charge of that compound. We could try this next one. Is going to be -2 for the oxygen, and then we would immediately be able to put parentheses around here, call this a 0, and realize that this should be +2 in order for that to work. Now from here, let's go ahead and make sure that we multiply all this by 3, so we should actually get 6 at the top there and +6 at the top there. We see that there's a total of -12 for the oxygen. Let's just keep that in mind. Let's go on to the right side here. This element is just going to be 0. Doesn't matter if we multiply that by 2. And over here, we're going to be sort of doing another parentheses thing here, because we've got O being usually -2. I want to multiply that by 2 because we've got 2 of them in there. But if we got that parentheses, this should be equal to 0, and therefore this should have a +4 charge. Otherwise, that wouldn't work too well. And let's multiply all this by 3 so that we get -12 on top here and a +12 up here, just to kind of keep track of everything in total. Now let's go back and see which ones increased their charge and which ones decreased their charge. The ones that increased got oxidized, the one that decreased got reduced. So if we look at the iron, this one started at +6 charge, but on the iron on this side is at 0 charge, therefore that thing got reduced. And so we'll put that over here. So we would say that the iron was part of this compound. So Fe2O3, that got reduced to straight up Fe. Now for the oxidized compound, let's try to notice the carbon up here. This one started at +6 on this side, and over here we actually have +12 on the carbon. So the carbon actually gained a bunch of charge. So we could say that CO becomes oxidized into CO2. Now we can make sure that this is actually accurate by counting up the points again. Let's see, this was supposed to be a +3 on that side and a -2 on that side. Then we'll multiply this out and we'll get a +6 on that side and a -6 on that side. If we compare that over here to this one, this becomes 0. So we've definitely gone from a +6 iron charge to a 0 iron charge. And for this side, well, let's see. So it's supposed to be a -2, it's supposed to be a +2. And over here, we got, technically this is a -2, we got 2 of them, so it's a -4. and this is supposed to be a +4. So we see that this carbon went from being +2 to being +4. So we've just more confirmation that this has been oxidized and this has been reduced. Now when something is oxidized, we say that it's basically lost electrons, because electrons have a negative charge. So you can see if you lose that negative charge, you're just going to be gaining charges. And we say that the reduced is when you gain electrons, and so therefore you're going to be basically becoming lower and lower charged. You're gaining negative charges, so you're losing charges. And you can try to remember this with the little oil rig acronym, because oxidized is lost electrons and the reduced is the gained electrons. So try to remember it like that. Now if we have determined that the iron 2 oxide has been reduced, and we have determined that the carbon monoxide has been oxidized, then we can also say that the iron 2 oxide was the oxidizing agent, and the carbon monoxide was the reducing agent, because these were the agents that caused that to be reduced. If it weren't for that carbon monoxide, that would still be iron 2 oxide. Because of the carbon monoxide, it transformed into regular old iron. The last type of common reaction is going to be the acid-base neutralization. We have something more like HCl plus NaOH becomes just regular old salt and water. So you kind of have this dangerous acid, and I mean, who knows what this base is going to do to you, but we have salt and water that you could just drink at the end. That's kind of crazy. But we have to kind of be careful about doing that in the right dosages. Now there's a cool way to find the concentration of a solution by using acid-base titration. So you'll be determining the concentration by neutralization, because we have a certain amount of acid, and if we put in enough base, it'll all turn into salt water. Put in too much base, then you can have some excess base. If you don't put enough, you're still going to have acid. So you got to do this at the right quantities. You'll have this thing called the titrant, which is going to be the known concentration, probably the base, but it might be the acid. And then that will be, you'll know the volume too in milliliters. And you'll also have the unknown concentration, whatever you're trying to figure out. It's the analyte. This will also be in milliliters. There's going to be an indicator that will change color once this whole reaction is basically completed. Now, if we know the concentration of one of these compounds and the volume of that, and we don't know the concentration of that compound, but we do know the volume, we should use the dilution equation. That just says molarity of one times volume of that one equals the molarity of the second one times the volume of the second one. So this should be able to instantly get you the unknown concentration. This is also going to be useful, let's say if you got some particular concentration and you're trying to achieve a specific molarity, you could also use this equation. Or if you're doing a serial dilutions, just over and over of the same compounds, and you do serial dilutions, that would work as well for the dilution equation. So this is pretty crazy stuff.